So I'd just personally like to extend my acknowledgement to the lands, sort of traditional owners of the lands on which I have done this research. It's quite a varied region. I've done a fair bit around both Mount Lofty regions, so the southern part of the basin, and up in the north as well. So I won't go through all the names here because Alan did that quite well. So the Neoproterozoic, just quick recap. So between 1 GA, so 1000 MA, to 538.8, that actually got updated officially as of the start of the year. It's divided into the Ediacaran and Cryogenian and Tonian. So the Cryogenian is one that Georgie and Ashley will speak to a bit more later. Basically, when we've got the big thought to be snowballs or slush balls occurring, so a big freeze in some sense. Sturgeon and Marinoan glaciations, so the Latin glaciation, are the two key things in that region, or in the region that that's known for. It's a really interesting time because we see the switch from prokaryote to eukaryote dominance. So there seems a really big shift in how life sort of was. Went from quite a foreign looking world to something more modern or on the way to what we see today. It's also where there's a pretty significant change in the levels of atmospheric oxygen as well. And it's also, as Wolfgang mentioned, the time when Virginia sort of was breaking up. So for the terminology aspect of things, so what the Adelaide Superbasin is really back to the original definition of the Adelaide geosyncline, so including these other sections where we've got the Cambrian, Arabian, and Stansbury basins, and then also the Neoproterozoic, so the Cumberland platform, which sits on top of the Curnamona province, Stuart Shelf on the Gawler, the Torrens Hinge Zone, which is kind of the boundary between that, and then the Adelaide Rift Complex, which is in the central area. So I guess the way I think of it is the Adelaide Superbasin is the point from when we had deposition in this basin system occurring from the breakup of Virginia right through to when the Delamerian is occurring. So it ceases the primary deposition within the Delamerian itself. So Virginia, in terms of what we think the continental configurations looks like, is something like this. So a little diagram I've got there. So for reference, Adelaide's about there. We think North Australia may have been somewhat rotated at this time. Antarctica is just this section here, and then this is Laurentia. So there's a few different models that have been suggested. This is sort of the sweat model, as it's known. It's likely that, I guess all the data is pointing to this one being most right. Obviously, they're all wrong because trying to reconstruct this stuff is really difficult, and the further back in time you go, the harder it gets. If you've ever seen the little diagrams and videos that Alan's involved with, Morgan as well, they go through, and Alan will make the point that they are always wrong, they're just the best guess we have. As for the stratigraphy, so the chronostrat aspect of things, this diagram here is what's showing. I worked on the Neoproterozoic section, so the Wirina and Preiss supergroups, which is sort of what Wolfgang was talking about before, so it's the Kurtman subgroup and stuff. There is also the Cambrian section, so the Morillana subgroup, which is divided up. Came into groups, and then a whole bunch of others there, so there's late forms for that. But I didn't really work on that, so I won't talk about that. As for the distribution of the surface rocks, that's what this is showing, so just a surface geology map. You see it's right over here into New South Wales. This is what's considered still part of the Adelaide Superbasin itself, so the Adelaide Rift Complex out here. This section's the Stuart Shelf mostly, Torrens Hinge Zone's effectively boundary along here. And then this is obviously the Flinders Ranges, Mount Lofty Ranges through here, so the main Adelaide Rift Complex itself. And then you've got the Davenport and Denison Ranges with Peak and Denison in Lyra. Just because I like to keep you all awake, here's some pretty photos I took. This is what it looks like on the ground. So two different sections around, so this one's actually at Arkaroola, and this one's actually a bit further over to the west. It's on the back of Mount Lyndhurst Station. The locals there affectionately know this as Tombstone country. It's actually the Wanaka Formation. It just forms like kilometre rings of effectively tombstones. They're about half the height I am. So I guess the take-home message of what I ended up spending 3.5 years doing was all the things that are coloured that aren't purple here is where I've added data in. So there's about 30 odd formations where I've added the trial zircon data to. I guess the other part of it was also going back and trying to summarise some of the literature and I guess bring us into a coherent point where we've built upon all the research that's been done prior and putting it into one position again, because there was quite a few stratigraphic revisions that had occurred since the last big chronostratigraphic framework had been put in place. Wolfgang was instrumental in that, but in terms of resynthesizing into one big thing, that happened again for a while. How does that all work? Well, these fancy diagrams, they're basically just statistics. So I go and zap a bunch of tiny little minerals called zircon, get numbers from them, and then throw them into these plots. What these ones here are kernel density estimates. All they're showing is the relative abundance on the y-axis, so the density against time. So going from present day down to 4 billion years ago. The higher that peak is, the more number of zircons are at that age in a given sample. And so we look at these trends through time and see if there's shifts. And from that, we can try and glean information about the change in the provenance, so the original sources of the sediment that's coming into the basin, whether that's through recycling of other basins or as a primary source. Obviously, the zircons themselves actually come from a primary source. You can't generate them in a sedimentary rock. You have to generate them in any sort of metamorphic setting. But they can go into a sedimentary basin and then move from there again as we go through. This other plot here is a similar way that uses a different statistical method to generate the intensity. So the color here, darker, is more abundant, so it's effectively just the peak. But with this, what we're able to do is look at the actual grain ages versus the inferred depositional ages and try and really tease out the differences in those plots. So we can see here it's pretty consistent for a while, and then we start getting an influx of younger zircons coming through. So that was effectively the first big portion of my PhD. And then that led to making some of these sort of maps. So I've got big arrows really showing generalized, I mean, very generalized direction, which I think the sediment transport's coming from into the central part of the basin. The purple line is just the outline of the overall superbasin. So I've got the Kalana groups, the oldest at this top left, and then going across to the Barrow group, Umberatna group, and Wolfgang group. So we're going from oldest to youngest. So you can see I've got changes occurring, and then the sizes are effectively trying to represent in a schematic way the overall domination of that given population. So if I think there's a lot coming from one area, it's a bigger arrow versus if I think it's got a minor contribution. And then you try and do these funky reconstructions. So this is my guess at what the Adelaidean system, well, I guess if we were standing here and were able to look at what was around us back at about, I think I did this at about 740 million years time, roughly, give or take 100 million years. This is what we think the configuration may have been like. I've got obviously the basements around and other Neoproterozoic basins in here and Mesoproterozoic. If you want to understand in more detail about that, I would recommend having a look at the paper because it's got a big caption, or actually like a whole paragraph to try and explain. But the key thing here is we think the ridge is somewhere off to this side, not really sure exactly where, but somewhere. And then I moved on to looking at things in a bit more fine detail. So here is data that I'm looking at from the oldest section, so the Arkarula and Kurtamerka subgroups. So it was a representative section based on previous work that had been done, compiling that into a graph, what we call a sedimentary log. So it's effectively a graph of the rock type through time. And then trying to think about it in a modern context of this tectonic sequence stratigraphy. So it's really just trying to think about base level change, take away the, I guess, the water turns in a sense. But effectively, if you've got a big hole, you can fill it up. If you don't have a big hole, you can't fill it up. That's kind of the main part. So it's trying to think about it in that sense. These are some of the, again, the little plots of the zircon distributions through time. Really interestingly, though, we found this particularly low, or the lowest unit in the Arkarula region, so the Shanahan conglomerate area. So theoretically, this is the oldest sedimentary rock in the basin. Had quite a different zircon spectra compared to the main parallel quartzite, which it's part of. Has the same main peak in it, but you can see there's basically all the old stuff's missing and there's a lot of the younger stuff sitting in here. And within that, we found this really interesting grain. So the first time I shot it with this hole here, half the signal that I got from the laser was really good and the other half was really quite garbage. So I thought I'll go and zap it again because there were a couple of other zircons roughly that age. And then I shot it here, came out perfectly as the first part of the signal, and then this one turned out really horrible as well. There's actually a tiny little inclusion you can see in here. I think there was some leakage and disturbance in the system. But what this did is it means that we've got the maximum depositional age, so the oldest possible age for this rock is now revised down to the 895 million years from 1100 million years, was the precursor before that, because this happens to sit under the Altana volcanics. So while it's probably close to the depositional age of that anyway, we really had a range of like 1100 to 830 was the actual numbers that we had. And then this last plot is I've heard Alan before, Morgan's favourite plot, but multi-dimensional scaling. They're a little bit counterintuitive when you think about them. But I guess the easiest take-home message here is if they plot close together, we're suggesting that they're more similar, so less dissimilar. It's really taking these kind of graphs and comparing how much they look the same. If they look really different, they'll plot really far apart. If they look really similar, they'll plot nice and close. And through this, we can actually try and start to quantify what we're visualizing in these other plots here. So we're actually putting some numbers behind how similar things are. So they become useful when we're trying to compare either rocks within the basin or to the original sources or to other basins as well. So in here, there's a few things from the Centralian Superbasin. And I've got some synthetic populations effectively as anchors of what were the main populations throughout the basin, and then some regions which are the magmatic sources for the zircons. So you can see it, Gawler Craton here, it's square within everything. So what that is saying that it's a pretty big component, which is what we expect. As you get towards the Centralian Superbasin, you see the Musgrave seems to be more similar. And again, that's something we would expect based on where things sit geographically. So from Wolfgang's diagrams earlier, I modified them a little bit. So this is effectively from that paper what we were thinking about in terms of how the basin evolved through time. So these are the main depot centres that we see. So this is where we actually have the exposures of outcrops. I haven't put in the inferred distributions, and that's something that sort of Wolfgang had shown before, particularly actually the Kurtenberger subgroup here, up on this side. So obviously, these may have been individual depot centres, but they may have been connected in some way. But there's a lot under the surface that we still don't actually know really what's there. These arrows are effectively representing the extension in a modern context of what we think it was. So it's not trying to reconstruct it for how it looked at the time, because it's very difficult to do. But if we were thinking about how it's extending and how it sort of sits in today's geometries, that was what it's showing. And so moving from the Kurtenberger subgroup into the Virgo group, we see a southward progression. And so that's something I'll talk about in a little bit as well. So I think on this slide, I start looking more at the Virgo group in itself. So this is actually covering stratigraphic logs from Adelaide, so Mount Lofty Ranges here, Arkaroola, I don't see that, but these are both North Flinge areas. So there is a fair bit of difference, and these little lines here are actually where the correlative stratigraphic units are. Obviously, this is one of those figures you really need to have a good look at. I don't think it'll show up particularly when I'll project it. But what it really means is that, say, this unit between these two lines here is the same as this one. It is the exact stratigraphic thing. So that allows us to sort of compare how things look across the basin. And then we've got the values again. So oldest bottom here, youngest here. This is actually a fair bit of this here is what one of our honours students did. So Erica van der Wolff. She went through and did a whole bunch of zircons. She was meant to actually go to work in New South Wales, but COVID stopped that. So she ended up doing some Mount Lofty Ranges stuff for me, which was fantastic for me. But one thing that's really remarkable that we found with that is for the majority of the sedimentary units around Mount Lofty, so right up to the basket range standstone, which is a fair way up, the detrital zircon spectra are almost unimodal, so they're very, very consistent. And then we just have a sudden shift just after you hit the Stonyford quartzite to something completely different. And these actually have quite a lot of young zircons that are pushing down towards the 700 MA. And then I've actually tried to line these up so that they're roughly equivalent. So this is in the south and this is up in the north. This is actually an amalgamation of a bunch of different samples covering sort of north up, which I'll split up further later to have a look at. And then the Gilbert Range quartzites, which is the equivalent of this here, and this is from around Clare. So we see the shift in the Scalability generally a little bit earlier in the north than we do see around Mount Lofty region. So it suggests there's some differences in the way that the rift is evolving as we're going through. And so this is where I started to look at that in a bit more detail. So I actually split off. So Scalability here, you've seen there's a few different ones, they're different regions. The grey are just data that had been pre-existing prior to the work I was doing in this paper, and the coloured things are the ones that I've done. There are some really interesting ones here. So the Copley quartzite, these particular samples here, they're actually from the same stratigraphic section at Copley. One is just at the very base of it, one's at the very top. The rock almost looks identical, barring like a few minor sedimentary features. So you pick it up and you wouldn't be able to tell where I grabbed it from. But the Zircon spectra and actually the Zircon morphologies are completely different. So this is actually meant to be a rock that is effectively the same thing. You're not really going much through time. You're probably a few million years at most. But this is a very remarkable change. And we see that it actually has an influx towards sort of what we typically think is sort of Musgravian, so 1180, 1080. But as we progress through into the Myrtle Springs in the same region, it actually pushes further down towards about 1 GA, which doesn't really fit with the Musgravians. So what we're sort of thinking may actually be something else out toward the northeast-ish. It's really hard to tell because we've got no idea what the basement is below there, but we do know that those zircons don't really come from Musgrave region. The only ages of that are either very far off into the sort of south in the kind of white area, or off in the Albany Fraser, which even then you don't see that sort of transport coming across. And we expect there's probably some sort of uplift occurring through Peterman area as well. So it'd be pretty hard to actually transport those zircons across unless they're airborne, which is possible, but the abundance of them would suggest that's not the case. The other thing that's really important about the borough is it's actually sort of a time where, if we're trying to work out what Laurentia is like and where it sits, that's where we really want to look. And that's sort of the crux with trying to do these linear reconstructions, is how we join up any continent to that part of Australia. Because it's probably the case that most of what was there is gone or has moved out. So the other suggestion for some of the sort of that 1GA is potentially the keel that's been hypothesized under New Zealand from oxygen isotopes in zircon, which suggests that they may be about the GA themselves. And it could be that that's part of the rifted microcontinent. But these little squiggly lines are comparing so Western Tasmania, so Jack Mulder, one of our academics here, has done a fair bit of work on that for his PhD and postdoc. Chump B in Laurentia, so this is some work that was done by Brennan, on the Laurentian side, in roughly where we think it is. And I'm just trying to compare how they look to each other. So there are some pretty big differences in this, but this is compiling all of the data from the basin itself. So it's not necessarily the best way to do it, but when you're trying to deal with so much data, it's kind of the only way to do it. But the MDS plot here is something that's a bit more useful in that regard. So the pinks are the Tasmanian stuff. The orange squares, these are the Laurentian sequences. So one of the things that I've sort of suggested in this paper, which I've got a preprint of at the moment, is that it seems as though Tassie probably stayed more towards the Australian part rather than the Laurentian aspect of it. Mainly based on the fact that the Tassie part looks more like Laurentia to start with, and it looks less like Laurentia as it progresses through time. And then it starts actually looking more like the Adelaidean aspect of things. So we think it probably stayed on that side. As for where Laurentia exactly is, somewhere east is about the best guess we have. So, bored you with a bunch of stuff there. This is the Tillite. So, Stubbs waterhole is just around the corner somewhere. So you can see here, there's these giant boulders sitting in just below them. So I'm going to talk about sturt formation. So arguably the now best constrained age-wise, thanks to all of these little things here. It has to be older than this 663 because there's a tooth in the Wolfgang, so we've actually got a point in time age. And it has to be younger than about 730, and that's based on the work that Erica did with the Borough group. So we've got detrital zircon sitting there at 730, which actually lines up really well with the thought to be sturdy. The rest of this figure is just all of the world's geotron for the sturdian. So it's a really good way of showing lots of it. It's not a great way of showing exactly where things sit in stratigraphy, and there's been a lot of arguments around the Laurentian aspect of things. There's a good chance that some of these are actually coming out and interpreted younger than what they should be based on the sort of doing Discordia fits to lead lost stuff. So there's a good chance they're actually a little bit older than what has been suggested. And these massive amounts of sedimentary logs are from the sturt formation right across the basin, and they look remarkably similar no matter where you are. It's effectively, you've got a boulder tillite sitting at the bottom, an interstitial region, which is normally sort of fine shales, can be sort of sands around the area. And then you head up into a slightly less boulder tillite sitting at the top. And then, so these are the toroidal zircon spectra from across the basin. Again, they're pretty similar no matter where you are, with the exception of a couple of little things in here. And then you have local influences from stuff that's nearby, so you'd be scraping some of the basement through the glacial processes. The other thing we did, so this is from one of the drill holes on the northeastern margin of the Stuart Shelf. Darwin did the actual analysis for this. So it's from a shale unit within what's thought to be the sturt formation there. There's two ages in this. One was from a different part of it, and really well. It's not radiogenic enough, so we get a giant age with there's probably some detrital components in it, which is called older. Obviously, it's got really huge uncertainties on it as well. But one of them came out kind of in the middle of where we think it is. So there's a good chance there is still some scattering here. But within the uncertainties here, it's probably representative of the depositional age of that shale. It may be at the upper end or the lower end, but it's a bit hard to tell given how large those uncertainties are. But it's one of the first we've been able to do. So that's only really thanks to a lot of the work that's been done here, trying to develop iridium strontium data in shales. And so here is kind of how the tillites all looked originally by their names. And so the revision we've done now is just that all of these tillites are part of the circulation. Now, this doesn't exclude things from being members later on based on some local differences, but this is just saying as a whole, that across the basin, the formation looks remarkably similar. It's bound in the exact same points in time. So we don't necessarily need to have a different name at formation level for every one of those. And then again, I'm just showing the directions of where I think most of the transports come from. So the pie graphs are just sort of distributions here. And you can see them sort of shedding in from that direction, which is pretty consistent with a lot of the paleocurrent data. The only exceptions up here, there's a little bit of conflict. So what do I think the overall evolution of Superbasin is? Much like Wolfgang actually, so propagated rift system beginning around 890 to 830 MA. Actually quite similar to the modern models for the East African rift system. So sort of exploiting some of the pre-existing structures there, so the Illyrian orogeny, which seems to be the case for most rifts through time. They really hit something that's already kind of weak by comparison. It's much easier to go for the plane of weakest area. Major extension events, so 800 to 780 up in the north, and about 740. So the 800 to 780 is sort of that bit I'm showing where the Copley quartzite was really having quite different toroidal zircon spectra, and that's sort of representative across the northern region. And then the 740 is when we're starting to see the change right down. There's probably some, well, there definitely is some extension within the Sturgeon as to whether it's the separation of the landmass to the side or whether it's maybe pulling off a bit more of the landmass with some intervening material. And then the Proto-Pacific Ocean opening up on obviously the margin or main margin of the Adelaide Rift Complex to the south, so effectively below the Kern and Mona, running that's the Nakara Q8 area. That would rile some people up. But that region. So if you think, well, I guess that way. No, that way. So away from the ocean in Adelaide. And it's likely that Laurentia in some form intervene in Continental block off to the east and northeast. This favourite photo that comes up for everything. So I'm really lucky Graham Heinsohn had me up to do some photography for one of the geophysics runs, and they took me up in a helicopter at one point. So this is actually the margin of the Adelaide Rift Complex itself. So you've got the Waltana stations just over here, Archelaus is back in here. That is Gammon Plateau. So that's kind of covering, what's that? About 500 million years you can see from there to there, and then if you add that, the remaining time since. And then just like to make a little acknowledgement, so particularly out of microscopy and Sarah, without Sarah, basically none of the work that I did during this or now would really be possible. And all the support we've received through, so both George and I have received over time. And with that, I will leave it.